Hi everyone. This is a recording of the fifth part of the analog math video series that I'm doing on circuits that can do mathematical operations. And today I'm focusing on a very important concept to move us forward, which is uh, putting things in the feedback of an op-amp to invert the function. So essentially, whatever function that we have that transforms a voltage to a voltage or a voltage to a current, we can get the inverse of that function if we just put it in the feedback of an op amp. For example, if we have a function that created a square, so for example, the input voltage is x and then the output voltage is x squared. If we want to create square roots, we can just put that function, the circuit that generates that function, into the feedback path of an op amp. And um, the output would be uh, a square root. Um, so I'll just give you a demonstration of this. Uh, so here I have an op amp wired in the non-inverting config, and here I have a simulated function. So this is imagine this is just some external some circuit here, and what it does is it takes the input, uh, which is the output of the op amp, O1, and it times by 5, and it outputs it here to the inverting terminal. So this is what a circuit that's multiplying the voltage by 5 is doing. And if I run the simulation, what I can see is the input is going from 0 to 1 volts, and the output is actually divided by 5. So it's the input divide by 5. So as you can see here, there is a 0.2 volt uh, at t equals 1 when the input is 5 volts. Why does this happen? Why is the op amp inverting the uh, voltage transformation in its feedback loop? Well, if you look at the perfected op amp and what it does, like a perfect op amp model, what it's doing is in steady state, both of these terminals have the same voltage and they have no currents. So uh, you can actually run a KVL on this loop, and you can see that whatever transformation going from the input, because this is the same voltage as the input, going from the input to the output has to be the reverse of whatever's happening up here, going from the output back to the input, right? So in order for this to work, the op amp must be transforming the voltage exactly in the opposite way that the feedback is transforming it because of KVL, the Kirchhoff's voltage law. And that is actually what you see when you put in any function in here. So I have a function that just multiplies it by 5, but if you have like an e, you'll get a if you get an exponential, if you use an exponential, you get a log, vice versa, vice versa. So essentially, what happens is uh, if this is f of x, where x is some voltage, and this is g of x, where x is some voltage, then um, f of g of x needs to equal x, right? That's essentially what the KVL law is telling us. Lastly, what is this, grounded tap over here? That's essentially just to allow the current to go somewhere, because the current cannot go back to the terminal. There's no current allowed in the terminals. So this resistor is to bleed off whatever voltage is at this point to ground and allow current to flow through it. And it actually does not impact the circuit at all. If we had a perfect voltage to voltage transformation in the feedback, we can change this resistor to like 10 ohms. And you can see it produces absolutely no difference. So here is the same graph again. Um, what it does do, though, is it regulates whatever current is going through the circuit. If the circuit doesn't care about a current range, then it's not going to impact the voltages at all. Um, so this brings me to the next point, which is we've seen a circuit that's like this before, right? The inverting amplifier. The non-inverting amplifier. So what is actually going on here is that this is a voltage divider put in the feedback path of a um, uh, of a non-inverting op amp. So here is a voltage divider, and what it's doing is it's basically dividing the voltage by two, right? And um, that means the op amp has to multiply the input voltage by two, and that's why we get the equation for the non-inverting op amp being what it is, which is in this case R4 divided by R3 plus one. Um, cool. So next, I want to talk about well, what happens if we used an inverting config? Like if we grounded the input and put grounded the non-inverting terminal of the op amp and put the input through the inverting terminal. Um, so what's actually happening here is that it transforms the voltage, the feedback path, into something that equates the currents. So when you have this configuration, um, the input circuit and the feedback circuit has to produce opposite currents. So because there's no current going through this junction, and because it's grounded at zero, you can set an input current through the input path alone, right? In this case, the resistor will drop whatever input to zero. So it essentially is dividing the input by the resistor value 100. Um, and uh, if you put in a voltage to current transformation function into the feedback path here, you can set the voltage by the input path, and again, KVL will run. It will mean that the op amp now has to transform um, whatever voltage transformation here has to reverse that transformation. So in this case, right, we have I equals the V, uh, the output voltage times 5, which means that here has divided by uh, output voltage is the current divided by 5, right, across this uh, op amp. And the current we can set by the input circuit because it's grounded. So here the current is going to be the input voltage, which is 0 to 1 volts, divided by 100, which gives 10 millivolts. And then this thing is going to divide it again by 5, which gives 2 millivolts. So let's see if that's true. So if we zoomed in here, we can see that, sorry, it's minus 2, that's right. Yeah, so it's minus 2 millivolts, as you can see, approximately. And the reason it's minus is obvious because the currents are facing each other. So whatever current here is the negative of the current here. So where might we use an inverting config versus a non-inverting config for inverting the feedback functions? Um, so with a non-inverting config, you essentially want to put in a function that's a voltage to voltage transformation. Whereas in inverting config, you want to put a voltage to current transformation. And we've seen this in the past in I think, Analog Math 3 video that I created where I showed log and anti-log circuits. Because the transistor has a voltage to current relationship, uh, it's basically e to the power of some VBE equals to the collector current. We can essentially use an inverting config to invert that to become a log amp. Um, Whereas here, today, I'm only using the voltage to voltage transformations for my circuits. If you want to dig into this further, you can look at the feedback characteristics of op amps. There's a lot of articles on those which tell you, um, you know, what happens when a feedback is in series or in parallel with an input and output of an op amp, and whether that becomes a current sensing current driver or voltage sensing current driver, etc., etc. Um, all right, so next I want to look at how to accomplish square roots. So as I said before, you basically just have to put a squaring function in the feedback loop of an op amp. And we know a squaring function from a previous video. That's the Gilbert cell. So if you input both inputs of the Gilbert cell as the same thing, it's going to square the value as the output. So I'm not going to draw the Gilbert cell in here, obviously, because it takes too much time. But I essentially put in a function that will simulate the Gilbert cell, which is with the both inputs being the same. And if we look at if we put in the feedback path, we can see that the output. Um, sorry about that. Uh, we need to run it again because it's scaled in now, zoomed in too much. So we have an input, and then we look at the output. You can see it's the square root of the input. And just to 100% confirm that, I'm going to square root the input manually to see if it matches the output. And if I go OK, there you go. It's exactly the same, right? Not going to go into this further. It's essentially just inversing whatever function that we put in the op-amp's feedback, and the function that we're putting in is the Gilbert cell that squares the voltages. So therefore, the op-amp will square root the voltage. Likewise, with division, um, we can achieve this by basically not tying both inputs of the Gilbert cell in the feedback loop. If we had one voltage fed in from the output of the op-amp, and then another voltage just fed in as an input that we can vary, then we get a division uh, circuit. So what this does is, imagine if we had a division input of N2, the op-amp is now, so the feedback path multiplies the output by N2. Therefore, the op-amp must take N1 and divide it by N2 in order to produce this O4 voltage. So if we look at the result here, let's see if it's correct. So we have a input here. So we have a input here from 0 to 1 volts, and another input that is from 0 to 2 volts. And we expect this divided by this to be equal to 0.5 volts, which is a constant all the way through. So let's see if we get that. And we do. So this is the what the op-amp is doing, which is outputting 0.5 volts. It's essentially divided by N1 divided by N2. So yeah, you can put in a Gilbert cell here and essentially connect one input to the op-amp's feedback, and then another input to a variable voltage. Awesome. So lastly, I want to talk about uh, a actual useful calculation, which is the RMS calculation. So just a summary, an RMS is basically if you have two values, it's a squared plus b squared divided by 2 or square root. And we use RMS to determine uh, basically to try and calculate the power of uh, what happens if we put in a AC signal through a resistor. Because an AC signal sometimes is centered at 0, if we just average the voltage, it's going to be 0. So for example, a sine wave centered at 0, it's going to give a 0 voltage on average. But obviously the power is not 0 because power is dissipated across the resistor regardless of if it's positive or negative. So in order to calculate the power, we have to basically take the RMS of the voltage and then multiply by the current in order to get the power. So, sorry, what I mean by that is V squared over R is the power, because the current itself is also determined by the voltage. So how do we calculate an RMS of a fluctuating voltage? Well, you can think of a fluctuating voltage as basically not just A and B, but A, B, C, D, E, F, G across many different points in time. And we essentially want to um, calculate it like A squared over some change in X plus B squared over some change in uh, X plus C squared over some change in X, etc., etc. And when it's infinitely small. So it's essentially like an integral that then divides by the X value, right? So it gives the average height of um, the squared uh, of the squared height. So how do we do that? Well, we first have to square the input voltage, so that's the squaring part, and then we have to average it by trying to find the DC voltage that exists across the square, and we do that by putting a low pass filter here, um, and then finally we square root that DC voltage again to find the RMS. So here in the input, I have a fluctuating sine wave from 0 to 1 volt, um, down to minus 1 volt. You can't see this in the graph because it's too zoomed out, but this is a sine wave. And like if I zoom in very close, you might be able to see it. So something like this. There you go. You can see it's a sine wave going up and down, up and down. And then, so we square this, right? It goes, so it becomes all positive. Now we average it uh, through this low pass filter. And the low pass filter, you need to design it in a way that the cutoff frequency does not include any of the higher harmonics of your signal. In this case, I only have one signal harmonic, which is the actual wave itself, the sine wave. But if it's a square wave or some other random signal, then your filter needs to be targeting a very low cutoff frequency and also have a very high uh, quality factor. So you need to pick these components for that. And then it goes into a square root circuit that we showed before to get back the RMS voltage. So let's see the result of that. I'm going to run this again to zoom the graph back out. So what do we expect? Well, we have a voltage that's that's a sinusoidal wave going up to 1 volt. So we expect the RMS to somewhere be around 0.707, which is 1 over root 2. And if we measure the output, is that actually true? And when it settles, we get a 0.708 volt. So it's very close to 707, good enough. Obviously, there are some losses, for example, across this resistor and the filter, and other factors. But overall, it's pretty close. It's pretty close to 0.707 volts. All right, so that's it for this video. And in future videos, I'm going to go over more concepts on analog math. For example, things like power calculations, derivatives, integrals, and piecewise functions, which can be used to create a universal function generator. Thank you.